Hi, so here is the third video for Engineering 311. And in this one, we'll be looking at scheduling and how you calculate the amount of water that should be applied. So, first thing to notice when we are looking at the calculations is evaporation. So, the evaporation is the loss of water, and that happens due to humidity, temperature, radiation, air movement, and altitude above sea level. Um, and so we can measure this, and the way in which we measure this is by something that's called an Class A evaporation pan. So basically, what we are doing is measuring the rate at which water evaporates out of a pan. And this pan is 1.22 meters in diameter and 250 meters deep, and the water surface is read off from a diagonal scale. So how this looks is you've got a pan that looks like this. So it is 1.22 meters in diameter and 250 millimeters deep, and it has a diagonal scale, something similar to a ruler. So water will be in this pan, and as this water evaporates, the quantity of water gets less, and the value that you read off from this scale becomes less and less. So if we look at a representation of the pan, scale, this diagonal scale that you see here, that's how it looks. And then that is how one looks if you would take a picture of it. So every morning at 8, roughly, you'll take a measurement, and then the next morning you'll take another measurement. And then after 24 hours, when you have a difference in value between the two measurements, you can calculate how much your evaporation is. So in this table, there are a couple of different values, and this column refers to the measurement that was taken, the previous one, and then that is the next morning. So what you'll see is this value over here that was taken afterwards is 34 millimeters, and then this one, this is the next row. So the next measurement is 51 millimeters. So the question is, what was the evaporation that occurred in that day? So you'll take the 51 and you'll minus it with 34, and then you'll divide that by 2, and you get 8.5 millimeters. Okay, so now the amount of evaporation was 8.5 millimeters. So you'll write that in. Okay, so then afterwards another measurement was taken, and you get to the next day, and the measurement that's taken is 78. So this value over here is 78, and you see another value which is rain. So the amount of rain they had in that day was 16 millimeters. And so the amount of evaporation that occurred in this day, so if this was the first example we did, this is number 2, you'll take that, just write in rain, so you'll take that 78 and say minus this previous measurement, which was that 67. So there's the 67 that I'm referring to, divided by 2 plus 16, which is this amount of rain. And shift that, and this will give you an answer of 21.5 millimeters. And so the amount of evaporation you had is 21.5 millimeters. So that is how you use a pan or class A pan to determine the amount of evaporation that you had in one day. So by just measuring the loss of or the loss due to evaporation due to the air, if you look at this pan, by just using that, you can then determine what the evaporation will be for a plant. So you have this formula. So you have ETC equals EO times F. So this ETC refers to the evaporation that happened in your crop, and then this EO is your class A pan. So the evaporation that you measured multiplied by F, and F is the factor for the crop. So by just measuring with your class A pan and multiplying it by the factor that is different for each crop, you can get the evapotranspiration or evaporation for your crop. And then taking everything of the last two videos together, we can now calculate how to determine the amount of water that you should use to irrigate. So the question is, determine the gross application rate of the two emitters, but in this case there's only one emitter A. So determine the gross application rate. So that refers to the rate at which water is flowing out of your emitter. And so the equation is gross application rate, or in Afrikaans you'd write bruto toedieningstempo, so or gross application rate equals the emitter deliverance, so the rate at which water is going out of the emitter, divided by the spacing of your emitters on your line, and then multiplied by the diameter. So to give you an example of what this looks like, if you've got a line, a dripper line, and here you have a hole, there you have another hole, and maybe another one. So in order to determine the rate at which water is being delivered to the plants or to the soil, that QE refers to the rate at which the water comes out of the emitter, and the LE, emitter spacing, refers to this, and then B, the diameter, wetted diameter, refers to that. So in this sum, in this question, we've got a the emitter delivery of 20 liters per hour. So you divide that by the spacing. There was a spacing of 1 meter multiplied by the diameter of 1.5, and you'll get a gross application rate of 13.33 millimeters per hour. So that is the rate at which the water is being delivered to the plant. So now the question is, determine the readily available water. So just from the previous or the first video, the soil water capacity is the water in the soil that can be used. So it's the water between field capacity and permanent wilting point, and the readily available water is the amount of water in the soil. So it's the soil water capacity multiplied by the effective root depth. So the amount of water in the soil within a specific area, in the area of the roots. So to calculate that, the readily available water, you can say readily available water equals soil water capacity times the root depth, and it will be 100 millimeters per meter multiplied by 0.8 meters. So the reason why we take that effective root depth over 2 meters is because you can see soil water capacity is millimeters per meter at the moment. So if you take this 2 meters, then your answer will be 80 millimeters. So just to make sure everyone understands what this means, soil water capacity is if you've got a block of soil, it is the amount of water, or it refers to the amount of water in this whole block between field capacity and permanent wilting point. So simply put, between full and empty. And then the readily available water, very simply put, is if you've got a plant with a root system like this, then the soil water capacity, if the soil water capacity is the amount of water for a whole chunk of soil, the readily available water is only inside that rooting zone area. That's just a very simple way of explaining it. So the net irrigation requirements, and that is the amount of water required or needed. So with the Class A pan, I said that evapotranspiration equals that measured value that you got from your Class A pan multiplied by F, which is the crop factor, and RE, the effective rainfall, is if you remember from the first video, the effective rainfall is the rain that ended up on the soil and that you didn't lose due to your leaves or any other reasons, runoff or seepage or anything like that. And that will be the amount of rain minus 20 divided by 2. So the net irrigation requirement, how much you have to irrigate, is that NAR minus your evapotranspiration minus your rainfall, effective rainfall, divided by the amount of days in the month. So net irrigation requirement per day in November. So in the month of November, your Class A pan said the evapotranspiration was 249, and you multiply that by your crop factor, which is 0.4, and then you minus your effective rainfall. So that would be your rainfall, which is 33 minus 20 divided by 2, and you put that on the amount of days in the month. So per day in November, your answer would be 3.1 millimeters per day. Then your theoretical cycle or theoretical cycles. So in a month, you are going to go through a couple of cycles to irrigate your crop. And in order to determine the amount of cycles, you will take, or the amount of days you have to irrigate, you'll take your readily available water. So that is the water available divided by your net irrigation requirements, which is the how much is needed multiplied by the area effectively. So B, if you remember from the first question, is the diameter, and LD refers to the spacing of the laterals. So if you've got two laterals and you've got your emitters on these laterals, then B refers to the diameter and LD is that value. So the readily available water, we can read from here again, is that 80 millimeters. So you can put that 80 in, divided by your net irrigation requirement, which was 3,1, multiplied by B. So B from this first one, you can see that value is the diameter, which is 1,5, divided by your lateral spacing, which is 2. And so the answer that you get for this is 19,35 days. So the theoretical standing time, how long will you let this irrigation stand for in order to fill up your soil, and that is your readily available water. So number 5 is your readily available water divided by your net irrigation requirement. Okay, and that is multiplied by your efficiency of your irrigation system. So if you have an irrigation system with an efficiency of 85%, then calculated readily available water was 80 divided by 13,33, which was calculated your gross application requirement, and then multiplied by your efficiency of your irrigation system, and that answer is 7,06 hours. Okay, so now that you've calculated that, you only have this two to calculate. So from this question at number 4, where it says the theoretical cycle was 19,35 days, in this situation, or mostly, you'll see that farmers divide their irrigation up into cycles of 7 days. So it will either fall in 7 days, 14 days, 21 days, or 28 days. So we'll look at the requirement, and you can see that it's 7,06 hours in a day. And if you think you've got 9 to 10 hours a day to work in, if you had to choose this 19,35 days, how many days would you put it in? 14 or 21 days? Because your cycle length is only a factor of 7 days, then you can say practically, so this was theoretical, but practically it will fall into a 14-day cycle in order not to over irrigate. And then because you are now using a 14-day cycle instead of a 19.35 day cycle, your standing time that you are going to let the irrigation run for is not going to be 7.06 hours anymore, but it's going to change to 5.10 hours. So how that works is you'll take your 14-day, which is your new cycle, divided by the old one, which was 19.35, and then you'll multiply that by 0.6 hours, which is the amount of hours theoretically, and that'll get you to 5.10 hours.